Let's extend the previous example now to calculating shear stress. This is the same T-shaped section that we've used in the previous example. The top box is 120 millimeters wide, 30 millimeters high. The bottom box is 30 millimeters wide by 50 millimeters high. We found previously that the centroid is 53.235 millimeters from the bottom of the box, or bottom of the shape I should say, and that the area moment of inertia is 2.2766 times 10 to the 6th millimeters to the 4th, or 2.2766 times 10 to the minus 6 meters to the 4th. Now if there's any problem at all with the metric system of measurements, it's this. Things that are human size, this box, this beam is around that big, give you either really large or really small numbers. Not really a problem, just something to keep in mind. In order to calculate shear stress in a beam, we need to identify a shear plane, the plane about which we're going to calculate shear stress. And so let's use this right here, the intersection between those two boxes. Okay. This is equivalent to saying that the boxes are perhaps glued, bonded, somehow joined together, and we're interested in what the shear stress is right across that interface right there. Okay. The governing equation for shear stress in a beam is this, VQ over IT. Right. V is the shear force in the beam, the externally applied force. For this example, let's use V of 100 newtons. All right, it's not very much. If you're more comfortable working in English units, there's about 4.45 newtons in a pound, so that's on the order of 85 pounds. The area moment of inertia is something we've calculated already. T is the width of the beam at the shear plane. We're interested in the shear across that segment right there, so our value for T is going to be 30 millimeters. Now let's work everything in meters and newtons. I found that if I do that up front, I tend to make fewer mistakes. So we're going to say that T equals 0.030 meters. All right, so far we've got B, we already knew I, we've got T. Now there's Q. Q is the first moment of area. It's an area times a distance. It's a little hard to give it physical significance, explain to you physically what it is. It's a term that shows up in equations a lot, and when the same term shows up enough times, somebody gives it a name. This is an area times a distance, so it's called the first moment of area. In figuring out the area moment of inertia, we use terms that look like areas times a distance squared. That's also called the second moment of area. So there's a consistent naming convention here. The first moment of area, capital Q, looks like this. Right. We use an area times a distance for all the boxes either above or below the shear plane. In this case, there's only one, so we only need one term in this series. It makes the problem a little easier. And the area we're interested in is the area of this top box right there. Well, that's easy to figure out. Okay, just base times height, and that's 0.0036 meters squared. Okay, so we've got that. Now, y is the distance from the centroid of this box to the centroid of the shape as a whole. Now, this isn't really to scale. The centroid of our box is a little above the centroid of the shape as a whole. So for us, y is going to be the distance of this centroid from base, which is 65 millimeters. And I'm going to write that in meters here. Minus that distance right there, which is 53.235 meters. So I'm going to write that also in meters. And that gives us 11.765 millimeters, or 0.011765 meters. So now we've got A and Y. Q is just the sum of A and Y, so it's 4.2354 times 10 to the minus 5 meters. All right, got that. So I'm going to write that over here. I'm going to have to erase some part of my board here. I don't have a whole lot of room. Okay, with that, we've got all the parts we need. So let's clear out some space and finish our calculation. Alrighty, so tau is equal to 100 newtons times 4.2354 times 10 to the minus 5, and that's going to be in meters cubed, by the way. Now, it's tempting to think of this as a volume. It's not. It's got the same units of volume, but it's really an area times a distance. So there's the numerator. The denominator is 2.2766 minus 6 meters to the fourth times our width, which is 0.030. Okay, let's just stop real quick and check the units. If the units are right, the numbers will mostly come along for the ride. So we have meters cubed up here, and we have what will be meters to the fifth in the denominator. So when we cancel all that out, let's see, we're going to get rid of that, make that a 1. And we're going to get newtons per meter squared. Well, that's right, that's pascals, that's the unit of stress in the metric system. Okay, so let's go one step further here and figure this out. If you work all the numbers out, you're going to get, let's see, I'm looking at my computer over here just to make sure I get this right. In the numerator, you get 4.235, and that's going to be in newtons. And in the denominator, you get 6.8, I'm going to read this, 299 times 10 to the minus 8 meters squared. Okay, that's the intermediate calculation. When you work that out, you come up with 62,013 newtons per meter squared, or 62,013 pascals.